All right, cool. Like discussed, in this video, we're going to look at ways to improve ML models using unsupervised learning. So the thing is, what we're trying to do here is there's so many use cases. There's so many data sets in the world, right? There's so many data sets in the world, especially when you look at very interesting use cases of machine learning, like text, video, speech data sets and stuff like that, so or images and all of that, right? So if we're going to solve AI's most ambitious problems, we're going to have to deal with data sets that are incredibly difficult to work with in supervised learning. And so we need to put in a bit of spice, a bit of unsupervised learning for us to capture the information in those data sets. But when we are trying to do that, so like when you're trying to capture that information in those data sets, data scientists face some very interesting problems. And these are the problems I'm going to discuss here. So yeah, I could have said 6 ways or 6 challenges. 6 challenges. And those challenges are mitigated by using unsupervised learning. So let's take a look at some of the challenges. Let's take a look at the challenges I'm talking about here. So number 1 is insufficient label data, and we discussed this in the previous video, where we said one of the strengths of unsupervised learning is it can work with insufficient labeled data. So what does that mean? Most of our data sets in this world are not labeled, and that means knowing whether something is spam or not spam. Like imagine the emails that you receive. There are some that are definitely spam. We know those ones with the lotto numbers and stuff like that. Or you have inherited money from a Nigerian prince or whatever it is. Those are known to be spam. But there are so many other emails that just come through the filters that are spam, but they are just not labeled as spam. So the machine learning model really does not know that this is spam. So when we have insufficient labeled data that we want to train a machine learning model on, what we can do, and yeah, I'm saying training a supervised machine learning model. So what we can do is we can use unsupervised learning. So let me talk about supervised learning. It needs sufficiently labeled data, but collecting this data could be costly, either time wise or money wise. Like imagine collecting all examples of spam emails. Where are you going to do that? How are you going to do that? Where are you going to get that from? So this is going to be costly time wise. Or if you pay people to give you their emails and label their emails, it's going to cost money to do that, right? So supervised learning, getting a lot of labeled data can be costly time wise or money wise. So here you can use unsupervised learning because you can automatically label data. So unsupervised learning can help you to automatically label data. It does this by analyzing the underlying structure, like we explained in the previous video. It analyzes the underlying structure. Let's say for emails, when it analyzes the underlying structure, it puts the emails into groups, and then it will say, okay, for this group here, you are grouped with labels that are spam, right? So if these emails are grouped with other emails that are labeled as spam, I'm just going to call all the other emails that are not labeled, I'm just going to call them spam, right? So unsupervised learning can automatically label unlabeled examples by clustering all examples and then applying the labels from labeled examples to every other example in that group. So in this group here, it will say, okay, dude, like I don't know what you are, but I have a few examples in this group that are labeled as not spam. So I'm just going to assume that every other example in this group is not spam. The same applies to this group here. You would say, okay, I've clustered you. You look like all these other emails that are labeled as not spam. So I'm just going to call you not spam to every other email in that group. So that is one way we can improve our models with unsupervised learning. So number two is going to be overfitting. I think this, if you have done supervised learning, as it is a prerequisite for this course, when you did supervised learning, you learned something called overfitting. So overfitting is when your model memorizes the patterns in your training data, and when it does that, it cannot generalize to unseen data or never been seen before data, right? And it usually is a result of the model learning an overly complex result. So the result it has its overly complex. Trying to get the spelling right here. It learns an overly complex model that is suited to the training data, but then when it comes to the test data or unseen data, it fails because it has crammed the patterns in the training data, right? So we can solve this by introducing unsupervised learning. In the unsupervised learning step, how we do that is the unsupervised learning, it will regularize the model. And regularization is a process of reducing the complexity. So it reduces the complexity of our model. It puts some punishment factors to reduce the complexity of the model, so that the model becomes a bit rigid and not too complex. We will discuss this in upcoming videos, but if you also watched if you took my Machine Learning for First Principles course, my first one, that was focused on supervised learning, we talked about regularization. We'll discuss it later. As it is part of unsupervised learning. So this regularization, it tries to capture the actual signal in the data. It tries to capture the actual signal in the data, and by doing that, it will make the supervised learning model much better. And the way it does that is we will take the data set, the original data set, right? So the original data set, it has its noise. It has its noise and a signal. Right? We'll put it through an unsupervised learning model. And this unsupervised model, it tries to extract just the signal. So it comes up with a new data set, or some people call it a new representation of the original data set. So now we have a new representation of the old data, and this should mostly have the signal and a bit of noise, but not that much. And this new representation is then fed into our supervised model. It's the one that will feed into our supervised model. So that new representation is fed into our supervised model. There is this step here that helps quite a lot, because if we feed this original data into our supervised model, it might lead to overfitting and stuff like that, which would be nasty. So you will do this step rather. Okay. So I'll just emphasize it, because we have reduced a bit of the noise, this supervised model is more stable and able to handle unseen data. And that reduces our overfitting. Number 3, we have something called Case of Dimensionality. Sorry, it's been months since I last wrote or used the pen and stuff. Nowadays we just use computers to type and all of that, so my handwriting is a bit bad right now. I know that, or terrible right now, so just forgive me, but hopefully when I'm speaking you can keep track of what I'm trying to write on the screen. So yeah, the Case of Dimensionality. The thing is, when we are modeling, right, with a supervised model, we're trying to create a way or a function in some dimensions that will separate the cases, that will separate this case and this case. So maybe in very simple terms, we are trying to create a line like this that separates this case and this case. But in high dimensions, That function is supposed to separate these cases, right? But it could be difficult because it's going to take into account all the features or all the variables or all the dimensions. So if we have 1 million dimensions, coming up with that function to separate these might be very difficult. And that leads us to the case of dimensionality, especially when we do not have enough cases or enough observations to support these 1 million features for the function to be created. It becomes very, very difficult when we have many dimensions or many variables. So sometimes it becomes difficult. Other times it's actually impossible. When it becomes difficult, maybe it just becomes time consuming for us to come up with a function, to come up with a function to search for this function. It becomes time expensive or computationally expensive. We just don't have the computational resources to come up with that function. So when that happens, we can use unsupervised learning to get rid of this case of dimensionality. What unsupervised learning is going to do is we're going to reduce the number of features to very salient features, number of features. We are going to reduce, let's say we have 30 features. We're going to reduce them to maybe 10 new features that actually capture the information in the 30, and then we apply our supervised learning model on these 10 new features. And now for the model to deal with 10 new features, it might be easier than the 30. Or from 1 million to 200,000 might be easier for the model to deal with because we have reduced the number of dimensions. And these new features that we have created, they usually they retain the information. That was there, that was hidden, that was there in the 30 features. The information that was there in the 30 features, it can be retained by the 10 new features. An example of this is PCA, Principal Component Analysis, or factor analysis. Another one is factor analysis. Very rarely have I seen people use factor analysis. PCA is used quite often, but these are two methods of doing this. We will see them in the upcoming videos. But the case of dimensionality, we have so many features. We just want to reduce them to salient features. We can use unsupervised learning through PCA, come up with new features, and then these new features are the ones that are fed into a supervised model. Those are the ones that are fed into a supervised model. So that's one way of doing that. Number 4, another problem is the problem of feature engineering. This is a huge problem, because when you start your machine learning model, if it's supervised machine learning model, for it to really work, you need to come up with the right features. Features are very, very important. If you do not have the right features, your machine learning model is going to struggle to separate your use case, your items or your instances. With the right features that capture the right information or the right differences between these two, your machine learning model, your supervised machine learning model is able to easily separate incoming data, new data. You'll be like, oh yeah, with the right features, I think you are actually an X and not a 0 or an O. You're not an O, you're an X or something like that. When you have the right features. But developing the right features is time consuming. It can be time consuming, needs creativity, and needs lots of domain knowledge. What features contribute to fraud? Okay, for those features, and then you develop new features. For example, if you're doing a model for Formula 1, for example, you need to understand Formula 1, you need to understand how cars work and stuff like that. Maybe your features that you have there, you just have distance and you have the time taken or something. That's all you have. So for feature engineering, you need to be someone who understands that you can create a new feature called speed. By calculating speed is equal to distance over time. Now you have a new feature, so you have engineered this feature. So you need to be creative, you need to have domain knowledge and stuff like that. Sometimes it is difficult to actually, and speed could be the most important feature. the one that is the most information for your supervised machine learning model, but it is one that you do not have in your data set. You have to engineer, so it might be difficult for you to do that. You can use unsupervised learning in such an instant. You can use unsupervised learning by coming up with a representation, by using representation learning, which automatically learns the right type of features to use to help you solve the task at hand. And this one here, this representation learning, you can use things like autoencoders. You can use autoencoders. Autoencoders help you. They will help you come up with new features that you might not think about. Because they come up with autoencoders. They are used. Let me write the name here. Autoencoders. They are used in automatic autoencoders. They are used in automatic feature extraction. Automatic feature extraction by representation learning. And these we are going to learn deeply about autoencoders and actually implement our own autoencoders, like the Boltzmann machines and stuff like that. Those are coming in an upcoming chapter. But I'm just saying, for feature engineering, just know that unsupervised learning can be used to come up with new features or to automatically learn new features without you having to crack your brain and stuff. You have to crack your brain, yeah, to some extent, but then you can make use of unsupervised learning to make the job much easier. Number 5, outliers. These things are nasty. Outliers are very nasty because outliers, they distort the patterns in your data. So what you can do is, instead of training an algorithm on rare distortive outliers, which increases the generalization error because maybe the incoming data doesn't have those outliers that you have in your training data, what you can do is you can use unsupervised learning to do outlier detection. You can do outlier detection, and when you have detected your outliers, you can put your outliers on one part, in one data set, and then your normal data in another data set. When you've done this, you can train a model on the outliers and train another model on your normal data. So when the data that then comes in, if it's in part of normal data, you apply this model number 2. If it fits in the outliers, you apply model number 1. And this outlier detection can be done with anomaly detection, what we are going to discuss in an upcoming chapter. Anomaly detection. When you detect it as an anomaly, it's an outlier. You then if you want, you can discard all outliers, but it's usually advisable to keep the outliers, especially the ones they are just outliers because the person swipes their card in the millions of rands. Rand is our currency here in South Africa, so don't be confused when I say rands. Some people can use dollars if you want. So in the millions of rands, but everyone else swipes in the thousands of rands. So the model will see that this behavior is an outlier. Don't discard it. It's a person who's it's not a wrong transaction. That's just how he has so much money. You know what I mean? So you can train a model for those high spenders and here for everyone else. Then the last one is also very important, which is called data drift. So if you remember, we said in our previous video, we said that supervised learning models work very well when the data doesn't change, when the patterns do not change. So supervised learning, they love it when there's constant patterns in the data. But sometimes the data will start drifting. Let's say you've changed your business model, or you've changed your target market, or whatever it is. There are things that just change. You've changed your consultants, and then now the data that you used to have is a bit different from the data that is now coming in. So there's a bit of data drift. You can use this introduces instability for a supervised learning model. What you can do is you use unsupervised learning. You can use unsupervised learning to come up with probability distributions of your data sets. So when you come up with probability, You can come up with probability distributions of your data sets, right? The new data and the old data. So this is old data, and then there's new data. And with unsupervised learning, you can compare these probability distributions. Are they still the same or not? If they are no longer the same, then there is data drift. When they are no longer the same, this model can automatically trigger a warning. Like, let's say, send you an email. You can send you an email to say it is now detecting data drift. And when it detects data drift, when it triggers that warning, you can then go and say, okay, cool, let me retrain my supervised model. And then you retrain it. Retrain the supervised model to fit the new trends that are in the new data set. Or you can do this as an automatic process. Usually it's better for you to look at it before you retrain. But if you want, you can trigger an automatic process to say, oh, if you detect a good enough probability distribution difference or a data drift, automatically retrain and stuff like that. But it will be good to do it as a human to keep track of everything. But you can, data drift is it's a real thing in modeling. Your supervised model, it needs constant patterns, but when the patterns start changing, your unsupervised model can detect that and tell you there is data drift and trigger a warning, and you can retrain. Think, for example, fraud. You train your supervised model on fraud, it works, but then the fraudsters out there, they start changing their methodology. When they start changing their methodology, the probability distributions in the new data that is coming into your model is going to be different from when you trained it 6 months ago, 12 months ago, right? And it's going to trigger a warning to say, we are seeing new patterns. Your model is going to stop working, dude. Your model is going to start failing. It's going to start failing because I don't know how to classify these new instances that are coming in. I don't know what they're talking about. And then you retrain, and then it works. So that's the power of unsupervised learning. All these, we are going to see them throughout the course. So I just wanted to emphasize those. And in the next video, we are going to just take a bird's eye view at unsupervised learning algorithms. Just take a look at unsupervised learning algorithms, bird's eye view. But as we go deeper into the course, those are the algorithms that we will be discussing. So stay tuned for that high level view.